Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement ridge regression from scratch and we'll demonstrate lasso from sklearn library. As you know, polynomial regression models are able to model the nonlinear relationship between features and labels. However, higher order polynomial models are prone to overfitting. There are two ways to tackle the problem of overfitting. One is training with more data and second is penalizing the weight vector through regularization. In this collab, we'll focus on point number 2. In the last collab, we tried to fix the problem of overfitting by training with more data. You can refer to that collab if you are interested in knowing more about it. In this collab, we will focus on penalizing the weight vector through regularization. Regularization, as you know, leads to change in linear regression loss function, which in turn results in change in gradient calculation. We will demonstrate the regularization on polynomial regression model. The change in regularization rate results in a new model. For different values of regularization weight, we obtain a new model. Thus, we have a problem of model selection at hand where we need to choose the best model among the list of candidate models. Finally, we demonstrate ridge and lasso solution path as a function of regularization rate lambda. So let us begin by importing necessary libraries for this implementation. We'll implement ridge regression from scratch using the NumPy library. We'll reuse the code for polynomial transformation and nonlinear data generation from polynomial regression collab. We'll implement ridge regression by making the following changes to the linear regression implementation. We can see that the loss function of the linear regression is this is a linear regression loss function, and when we add the ridge regression penalty, we add this term which is shown in the blue, which is lambda by 2 W transpose W. This leads to the change in the gradient calculation. The gradient calculation now has an additional term of lambda W. And when we try to learn the regression model to normal equation, we add one more term which is lambda into identity matrix to the normal equation. So the changes that are needed in linear regression are shown in the blue color. We'll reuse the linear regression class implementation. We first make the change in the loss function. This was the original implementation of the loss function. Now we add the term which is lambda by 2 into W transpose W. It also leads to change in the fit function. So in the fit function, now we add the regularization rate lambda into the identity matrix. And identity matrix has the size which is the first dimension of the shape of X, which is the feature matrix. And what is this dimension? The dimension of the feature, the first dimension of the feature matrix is number of features. It also leads to change in the gradient calculation where we add a term which is lambda times W. And another thing that we have added is we have added this regularization rate as a parameter to each of these function in calculate gradient, uh, in fit, and also in the loss we added regularization rate as an additional parameter. Now that we have a linear regression implementation modified for ridge regression, let us test some of these functions that we modified. There are a couple of functions, loss and gradient calculation, that we would like to test. For this, we use exactly the same configuration that was used in linear regression collab. Additionally, we have regularization rate, which is set to 0.01. Now what we will do is we will try to hand calculate the value of the loss with this regularization rate of 0.01, and we know how to calculate the loss. It is half, this is the predicted value of the label minus the actual value. We take transpose of that, we multiply it with again the same difference vector of the predicted value and the actual value, and we add a regularization term, which is the ridge regression regularization term, which is lambda by 2 W transpose W. So what we do is we substitute each of these values to the variables, corresponding variables, and we have this equation. We have calculated this equation in a step-by-step manner in the linear regression collab. Here we directly jump to the solution step. So the algebraic manipulation leads to the answer of 62.52 for the loss function. We test the loss function with this setup that we use to hand calculate the value of the loss. We set the regularization rate to 0.01. We set the feature matrix, weight vector and label vector to the ones that were used in this calculation. And we write the expected loss to 62.52 as we obtained from our calculation. We calculate, we instantiate linear regression object and we call the loss function on the linear regression object with feature matrix, label vector and regularization rate as parameters. We check the shape of the loss and we also make sure that the expected loss is indeed equivalent to the loss that we obtained from this particular function. And you can see that the test passes. Next, we perform the gradient calculation test. Again, we use the same setup for the gradient calculation step. And you can see that we substitute the values for the feature matrix, the weight vector, the label vector, the regularization rate and the weight vector. And then the matrix vector calculation and algebraic manipulation leads us to the gradient vector of 15.01, 105.01, 50.01 and 95.01. So you can see that the original feature vector without regularization was here. We added the regularization term or the weight penalty term through this calculation, and that resulted into the new gradient vector. And if we test the gradient calculation with this setup, we can see that the test passes. So now that we have implemented the changes that are needed in linear regression model for imparting the ridge regression functionality, let us use the modified linear regression code or the ridge regression code for fixing the overfitting problem in polynomial regression. Here we generate 10 samples from the nonlinear function, the relationship between x and y, the feature and the label is generated by 2 pi sine of 2 pi x. So we use a sine 2 pi x as a function for generating this data. And remember, we have a single feature here, which is x1, which you can see on x-axis, and the corresponding y value is on the y-axis. The green line over here is the function that was used for generating this training data. And the blue circles over here are the actual training points. These training points were added by performing the sign calculation on the value of x1 and then adding some noise which is controlled to this particular parameter. So this is the training data, and we would like to learn a regression model that maps the input feature x1 to y. And as you can see that the relationship between x1 and y is nonlinear, we'll use the polynomial model. First, we use polynomial model without regularization so that you can see or you can recall what kind of fitments we were getting. We have seen this in detail in the polynomial regression collab. Here what you see is there are 6 different figures or 6 different polynomial models that we have that we have trained. The first polynomial model was trained with degree of polynomial to be 0 and the regularization rate equal to 0 or lambda equal to 0. So you can see that we have not used any regularization, so lambda is 0 for all the models. We vary the degree of the polynomial in order to fit different polynomial regression functions. Here we use polynomial of degree 1, here it is polynomial of degree 3, then here it is degree 5, degree 7 and degree 9. And you can see that since we have not used regularization, the polynomial functions, the polynomial regression models with degree greater than or equal to 7 tend to overfit. You can see that here in case of degree 9, the polynomial regression model is literally connecting the training points. So this is a sign of overfitting, and we have talked about it in great detail in polynomial regression collab. Now what we will do is we will try to add regularization and try to control the overfitting problem. So let us run the polynomial regression with ridge regularization with regularization rate of 0.01. Let's look at the code. So here what we do is we first perform the polynomial transformation of the given degree and then we apply the linear regression model. Here, while applying the linear regression model, we are also setting the regularization rate to 0.01. Now you can see that as we added the regularization rate, it seems that the model, the polynomial regression model with degree greater than or equal to 7, they are now not that overfitting. You can see that polynomial model with degree 9 was literally connecting the points. If we go up and see here, they were literally connecting the points, right? Now you can see with regularization rate added, the model is not overfitting now. It is much smoother compared to the solution without overfitting. Now what we will do is we will fix the degree of the polynomial regression model and vary the regularization rate to see the effect of the regularization rate on the polynomial model. So here we loop over different regularization rates. You can see that we have fixed the degree of the polynomial to 9 and we vary the regularization rates. Here we have used a small regularization rate of 0.001. Then here we have used slightly larger regularization rate of 0.01, then this is 0.1, 0, then regularization rate of 1 and 10. So we have increased the regularization rate by by factor of 10 in the top row and also in these two cases. And here we have used the regularization rate of 0 to demonstrate what was the fit in the original polynomial regression model without regularization. Now you can see that as we increase the lambda or the regularization rate, the polynomial fit is more and more smoother, right? So you can see that here there is no regularization, so this fit is wiggly, right? There is a lot of ups and downs here, but you can see as we apply even a small regularization rate, this curve has smoothened out, right? And as we increase the regularization rate, the curve become more and more smoother. But you can also observe that too much of regularization is also not good. So you can see that regularization rate of 1 and 10, they are pretty much underfitting, right? Because you can see that the model which is shown by red, the model fitment. So this model fitment is far apart from each of the training points. So there is the training error is high in this particular case where we are using regularization rate of 1, as well as in this case where we are using regularization rate of 10. So we'll have to be careful in terms of using regularization. Too much regularization is also not good, and too little regularization is also not good. So if we do not use any regularization, we experience the phenomenon of overfitting. And if we use too much of regularization, we experience the phenomenon of underfitting. So there are these two extremes of overfitting and underfitting, and we need to choose the regularization rate which is in between these two extremes. And that's what we do with model selection. As we change the value of the regularization rate lambda, we get a new model. Now if we use different values of lambda, we will get different models. So which model to select? And that's where model selection helps us. So we first fix the list of lambdas that we want to experiment with. We divide the training data into training, validation and test. For each value of lambda, we train the ridge regression model with lambda for the training data, and we calculate training and validation errors on the trained models. We select the models with lowest training and validation loss among all models. So the model that gives us the lowest training and validation loss, the corresponding lambda is probably the best lambda for the ridge regression for this particular data set. We use some of the model selection helper functions from polynomial regression. We have modified them suitably to suit for our needs in ridge regression. So we define a weight dictionary, training error and validation error dictionaries. And here for every regularization rate, we store the weights that we obtained from the run of ridge regression fitment, and then we also store the root mean squared error on for that particular model on training set as well as on the validation set. And then we plot the learning curves with lambda, the regularization rate, on x-axis and RMSE on y-axis. You can see that if we use too much of regularization, both training and validation errors are high, and this is a typical sign of underfitting of the model. Whereas if you come to the other extreme, where we are using very small regularization rate, you can see that there is a sign of overfitting, where first the training and validation error went down, training error kept going down further, but validation error has gone up after a certain point. So here we have to choose the point, the model that has got lowest training and validation errors. So probably this particular point seems to be a good point. 10 raised to minus t, the value of lambda, has lowest training and validation error. After that, the validation error has started going up, or even this point, right, 10 raised to minus 5, but the gap is something which is worrying, right? Gap is a bit more. So you choose this point or this point, but beyond this point there is clear-cut sign of overfitting because the validation loss seems to be going up. Let us plot the changes in the weights as function of lambda, the regularization rate. We have lambda on x-axis and we have weights on y-axis. Since we have trained a polynomial regression model of degree 9, we have exactly 10 weights over here. Generally, while applying penalty, we ignore the bias term. But here we have also included the bias term for along with other weights. So you can see that as we reduce the value of lambda, or as we reduce the regularization parameter, the weight vectors or the weight values increase. Here, when we are using a very large lambda of 10, we saw that here there is an underfitting phenomenon, and when there was underfitting, most of the weights were close to 0. And as we reduce the regularization rate, the weight starts increasing. So over here you can see that there are many weights are non-zero, and as we reduce the regularization rate further, let's say 10 raised to minus 3, you can see that many weights are now greater than, or many weights are mostly non-zero here. And when we reduce it even further, you can see that certain weights have literally exploded. They have gone as big as 20 and minus 20. So you can see that as we reduce the regularization rate, there is a risk of overfitting. You can see here, right, in this particular curve, we discussed the overfitting problem. And in the polynomial regression collab, we have seen that whenever the model overfits, the weight vector has large values in it, which is what you can observe in the right side of the plot. As we reduce the regularization rate, most of the weight values have exploded. So you can use either of these plots to decide which is an appropriate value of lambda. So maybe the value of lambda around 10 raised to minus 3 seems to be appropriate value of lambda, because you can see that even in this particular figure that weights have not exploded that much when we are using value of 10 raised to minus 3, as against the value of 10 raised to minus 5 for the regularization rate. So this was about implementation of ridge regression from scratch and how to select the appropriate ridge regression model with the appropriate regularization rate. In the next video, we'll implement or we'll demonstrate lasso regression model. We'll not be implementing the lasso regression model from scratch, but we'll be using it from the sklearn library and demonstrate various aspects of lasso regression model.